Hello, my name is Sanjeev Mahajan. I am Associate Professor at Beyond College of Engineering and Technology, Department of CSE, Gurdaspur. The topic of my lecture is framing, error detection and correction. The contents of my lecture will be framing, types of errors, error detection, error correction. Framing and error control are the design issues of data link layer. Now, first we will discuss framing. Frames are the small data units created by data link layer. The process of making frames is known as framing. The physical layer gives data, raw data to the data link layer. Then data link layer makes frame from that data. Similarly, at sender, network layer gives packets to the data link layer, and data link layer further makes frames and apply error detection and correction and other flow control to those frames. How frames are made in data link layer or how framing is done? Various framing methods are character count, character stuffing, bit stuffing and physical layer coding violation. These are the four main framing methods which are employed by data link layer to make frames of the data. Now we will discuss all these methods one by one. First is character count. In this method, a special field in the header frame is used that specifies the number of characters present in that particular frame. Character here means the number of bits. So in the frame there is a header field and then data field. In the header field, how many bits are there in the data field are specified. Here is an example. Now frame 1 has 3 bits or 3 fields. First field shows the header. It contains 3, which means there are total 3 fields in the frame number 1. In frame number 1. So first field is header field and next two fields are data field. Similarly, in frame 2, header has 4. Header contains 4. This means there are 4 fields in the frame. Similarly, in third frame, header contains 7. This means there are 7 total fields in frame number 3, and 1 is header and remaining 6 are data field. In frame number 4, header contains 2. It means there are total 2 fields in frame number 4. This is the simplest method of doing framing, that is called character count, but it has many limitations. If the header information is lost or altered due to communication error, then the entire synchronization of the frame's boundaries is lost, as shown in the following example. Now in this example, there are 2 pictures A and B. In A, there is no error. There are 4 frames. First frame contains 5 characters, second frame contains 5 characters, third frame contains 8 characters, and frame 4 contains 8 characters. Now we are looking at A. Frame 1, the header field contains 5. It means there are total 5 fields in frame 1. Similarly, in frame 2, there are 5 fields. Frame 3, header contains 8. It means there are 8 characters in frame number 3. In frame 4, header contains 8. It means there are 8 characters in frame number 4 also. Now, in case the header information is lost because of communication error, as shown in figure B. Now, suppose frame number 2's header information is altered. It was previously 5, now it has been changed to 7. What will happen? Frame 1 is okay. Frame 2, now header says it should contain 7 characters. But actually, if the error has not occurred, then it should have 5 characters. Now actually it should have 5 characters, but now header specifies that there should be 7 characters. Now what will happen? The information is lost. The frame 2 boundaries are lost. Now frame 2 contains 7 characters. Similarly, the frame 3 contains now 1 character as per figure B, because header information contains 1. Similarly, next frame will contain 2 characters. So entire information is lost. All the frames will be erroneous. So these frames has to be retransmitted because framing information has been lost. This is the main problem. This was the main problem in character count, that the framing information is lost and no one can judge or identify from where the information has been corrupted. Now, the second method is character stuffing. In this method, each frame starts and ends with a special character that marks the beginning and end of the frame. Instead of having a field specifying number of characters, in character stuffing, the frame starts and ends with a special character that marks the beginning and end of the frame. What is the special character? Frame starts with DLE STX and frame ends with DLE ETX. DLE means data link escape and STX is start of text, whereas ETX is end of text. In fact, the ASCII codes of DLE STX and DLE ETX are used to mark the boundaries of the frame, as we have shown in this diagram. DLE STX means start of frame, DLE ETX is end of frame, and in between these two there is data. So whenever there is DLE STX ASCII code, it means there is a start of frame, and whenever there is DLE ETX ASCII, it means this is end of frame. Now this DLE STX or DLE ETX can come in the data also, because what is DLE ETX? This is a bit pattern. Same bit pattern can be there in the data. Now what will happen in that case? In character stuffing framing, the data similar to ASCII code of DLE ETX may be misunderstood as end of the frame. To avoid such happenings, if there is code of DLE in the data, another code of DLE is stuffed by the sender's DLL. DLL is data link layer. So if there is DLE code in the data, then that code is repeated by the sender, so that this should not be misunderstood as end of frame. More than one DLE code is never treated as end of frame or start of frame by receiver. The receiver's DLL destuffs the duplicate codes of DLE in the data. Now here with an example, the character stuffing is explained. Suppose the data is 1101, then DLE code, then 110. DLE code can be some bit pattern. Now to make frames of this data, DLE STX will be added at the start and DLE ETX will be added in the end. But instead of just adding data itself, one more DLE code that is shown in red color is also added by the sender. So receiver, when receives this frame, it destuffs DLE, which was stuffed by the sender's data link layer, and this is not treated as end of frame or start of frame, because there are multiple DLEs. If there are more than one DLE, it is never treated as start of frame or end of frame. So after receiving this data, one DLE is destuffed by the receiver. Now third method is the best method out of all the framing method, that is called bit stuffing. The problem in character stuffing was DLE STX and DLE ETX has to be added with each frame. So number of redundant or unnecessary data has to be added. So overhead of the data transmission is increased. Now in case of bit stuffing, only one byte is added before the frame and one byte is added after the data in the frame. That byte is called flag byte, which contains 0, 6 times 1, then 0. This is called flag byte. Now this flag byte is added before and after the data to make a frame. For example, if data is 1010, 111, 0011, this is data, then frame will be as enter. This flag byte will be added before the data, and similar flag byte or same flag byte will be added after the data. No, the problem remains the same which was there in byte stuffing or character stuffing, but that this type of pattern may be repeated in the data. So the sender's DLL data link layer takes care of this, that this type of data should not be there in the this type of byte should not be in the data itself. If there is data of similar pattern, then that has to be taken care by the sender's DLL as shown in the example. The problem arises when there is data same as flag byte. The problem is handled by stuffing bit in the data that is similar to character stuffing. If there are 5 consecutive binary ones in the data, a binary 0 is stuffed by the sender's DLL, because in the flag byte there are 6 ones. Now, if there are 5 consecutive one 0 is automatically submitted by the stuffed by the data link layer of sender, so that 6 1 should never appear in the data. And this binary 0 which is stuffed by sender is destuffed by the receiver. The extra stuffed 0 bit is removed or destuffed by the receiver's data link layer. Here is the example. The data is 0 1 0 1 0 0 1 1 1 1 1 1, though 6 times 1 0 and 0. This is same which is the pattern of flag byte. Now 5 times 1, after 5 times 1 is 0 is stuffed. Now remaining data is same, this data is same, and after 5 times 1 0 is stuffed by the sender's data link layer, so that there should never be 6 times 1. Now this stuffed bit is destuffed by the data link layer of the receiver. Data received by network layer on receiver side after performing destuffing by data link layer. Now after destuffing the data will become same. This data and this data are same. This data and this data are same, because this was stuffed at the center side and at the receiver side this is destuffed. Why this was stuffed? So that this should not be misunderstood as end of frame. So this flag byte should not appear in the data. So after 5 consecutive ones 1 0 is stuffed. If there are 5 consecutive ones in the data, then 0 is stuffed in bit stuffing after 5 ones by the sender's data link layer. Here is one more example. The original data is shown here A. Now after 5 ones 0 is stuffed, after again 5 ones 0 is stuffed, after again 5 ones 1 more 0 is stuffed. Now 3 zeros are stuffed, because this data contains many ones 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So 15 ones are there. So after each 5 ones 0 bit is stuffed. Now the data link layer of the receiver destuffed these zeros which are appearing after 5 ones. Now A shows original data, B shows the data as they appear on the line transmission line, and C shows the data as they are stored in the receiver's memory after destuffing. Now last method is physical layer coding violation. This last method of framing. This framing method is used only in those networks in which encoding on the physical medium contains some redundancy. In some lanes, each bit of data is encoded by using 2 physical bits. For example, in Manchester encoding, bit 1 is encoded as high-low pair, whereas bit 0 is encoded as low-high pair. This is shown in the diagram on the next slide. Now, what is written here is that some physical layer coding is not 0 as 0 and 1 or 1 as 1, but 0 as 0 1, 1 as 0 1 0, 0 as 0 1, 1 as 1 0. For example, in Manchester encoding, 0 is 0 to 1 transition, 1 is from 1 to 0 transition in between the pulse. 0 to 1 transition, 1 to 0 transition, 1 to 0 transition, 0 to 1 transition, for 0, 0 to 1, for 1, high to low, for 1, high to low, for 0, low to high, for 1, high to low, for 0, low to high. Now, this 0, for this 0, the combination is low high, for this one high low, low high, high high, high low, then low high. So 0 is low high, 1 is high low. So how framing can be done? In this framing method, the frame begins and ends with such bit patterns which will never appear in the data. Frames in case of Manchester encoding can start with high high or low low pair, because high high and low low pair will never appear in the data, because 1 is high low and 0 is low high. This is the simplest framing method, but the best method out of all these 4 is bit stuffing, because it has minimum overhead and it can be used very efficiently. Now next after framing is error control. Data can be corrupted during transmission. Some applications require that the errors be detected and corrected. In case of computer networks, data should almost always be error free. Real-time video, real-time data can be erroneous, like if you are watching a live TV match, then some frames may be in error, then it's not required to repeat those frames. But in a computer data networks, the data transmission should almost always be error free. If there is error, then data has to be retransmitted or corrected. Now before correction, detection is necessary. How error detection can be done? Enough redundancy is added to detect an error. The receiver knows an error occurred but does not know which bit is in error or which bits are in error in case of detection. In case of correction, receiver also knows which bits are in error, so accordingly those bits can be made error free. How bit errors can occur? 1 will become 0 or 0 will become 1. How this can be corrected? Make the adjustments. If 1 has become 0, make it to 1. If 0 has become 1, make it to 0. Error detection has less overhead than error correction, because more redundancy has to be added for error correction. For error detection, less redundancy has to be added, so it has less overheads. What type of errors can occur in data communication? There can be basically 3 types of errors: single bit error, multiple bit error, and burst errors. In a single bit error, only one bit in the data unit is changed. Now here single bit error is shown. Only one bit of the data is changed. Change means it will either become 0 to 1 or it will become 1 to 0. If original bit was 0, now it has become 1. If original bit were 1, it should have become 0. Only then there will be single bit error. Because in case of binary, there are only 2 states. One is 0, the other is 1. So single bit error will always occur if a bit is changed from 0 to 1 or from 1 to 0. In case of multiple bit error, more than one bit has changed or is changed. Now in this case there are 2 errors, so it is called multiple bit error. A burst error means 2 or more bits in data have changed, but they are changed at consecutive locations. The difference between multiple bit error and burst error is, in case of multiple bit error, more than one bit is changed, but they are not changed at consecutive locations. When more than 2 bits are changed and at consecutive locations, then it is called a burst error. Here there are 5 bits which are changed because of burst error. 0 have become 1 and 1 has become 0. So more than 2 bits are changed at consecutive locations, so it is called burst error. To detect or correct errors, there is need to send extra bits with data. These extra bits are called redundant bits. The structure of encoder and decoder in case of error detection will be like this. The message will be encoded and some generator function will be used to add redundancy or some bits with the original message. That redundancy will help at the receiver side to check the error, and if there is error, then that particular frame or data is discarded and retransmission from the sender is requested. Now at center side there is encoder, message generator, and message with redundancy is transmitted on unreliable transmission, because the communication paths are always unreliable. Noise can be introduced because of many factors. Now received information is further checked, and if data is okay, some syndrome value is calculated, and according to that syndrome value, if that syndrome value is 0, it means data is okay, and if that syndrome value is non-zero, it means data is erroneous, and accordingly measures are taken to retransmission of data or correction of data depending upon whether it is a error detection code or error correction code. Now same thing is explained here also. So the original data was 101 0 0 0 0 0 0 0 0 1 0 1 0 1. A generating function was used to calculate redundancy. Now this redundancy is added with the data. This can be added in the header, this can be added in the tailor, it can be added in between. It depends upon which code of error detection one is using. Now this data along with the redundancy check is transmitted on the communication path. This communication path is always unreliable. Now at the receiver a checking function is used, and depending upon this checking function and the data received, if the data is correct it is accepted, and if it is incorrect or erroneous it is rejected. There are various error detection methods, and some of those which are more common are VRC, LRC, CRC and Checksum. VRC stands for vertical redundancy check or vertical redundancy code. LRC stands for longitudinal redundancy check. CRC stands for cyclic redundancy check. VRC is also popularly known as parity code. In this, the overhead is very small. Only one bit of redundancy is added with the data. Now that bit is calculated depending upon the number of ones in the data. If number of ones are odd, then that bit is 1 if even parity generator is used. In case of odd parity generator, that bit will be the redundant bit will be 0. Now we have used in this example even parity generator. What even parity generator does, it calculates the number of bits in the data. If number of ones in the data, if number of ones are odd, then parity will be 1. If number of ones are even, then the parity will be 0. In our example data, number of ones are 3. So to make it even, redundant bit will be 1. So number of ones are odd, so our parity bit is 1 or redundant bit is 1. Now this data is transmitted to the receiver on the unreliable communication path. Now again the receiver checks whether the data has now even number of ones including that parity bit. If the data has even number of ones, then the data is treated as correct, otherwise it is treated as incorrect. But the problem is, if more than 2 data bits are changed during transmission, again the parity calculation will be correct, because suppose 2 bits are changed, then parity bit will be 1, because again after changing 2 bits number of ones will become again odd and parity will be 1. How come receiver comes to know that there is error in the data? So a simple parity check code is a single bit error detecting code in which size of code word is equal to size of data word plus 1. Even parity ensures that a code word has an even number of ones, and odd parity ensures that there are an odd number of ones in the code word. Now it is explained with generator, encoder and decoder, checker in the decoder and generator in encoder. A single parity bit is calculated by generator and added in the data, and it becomes a code word now. Data word plus parity bit is code word. It is transmitted on unreliable transmission communication path, and this code word is again interpreted or checked by the checker function, and syndrome is calculated. Syndrome is, if there are parity is true, syndrome is 0. If the parity is not true or false, the syndrome is 1, non-zero. Syndrome is 0 if the parity is true, syndrome is non-zero if the parity is false. Now at the receiver side, if syndrome is okay, then or syndrome is 0, it means data is correct and it is accepted. If syndrome is non-zero, it means data is incorrect and it is discarded. But the problem is, if there are more than one error in the data, if there are 2-bit error or 4-bit error or even bits error, then the data will be not checked for its error because the parity will remain same or syndrome will remain 0. So data will be misunderstood as data is correct whereas the data is incorrect. Let us look at some transmission scenarios. Assume that the sender sends the data word 1011. Now D0 is data bit 0, D1, D2, D3. Now this data is transmitted 1011. The code word created from this data word is 10111. Now one more bit is added, this is parity bit. Because number of ones are odd, parity bit is 1, we are using even parity system. In even parity system, the total number of ones after including the parity bit should be even. Now this data is sent to the receiver. Now we examine 5 cases. If there is no error, the received code word will be same. The syndrome is 0, the data word is created. If single bit error has occurred in D1, suppose D1 is changed from 1 to 0, the receiver code word will be 10011 because this bit is changed and this is parity bit. The syndrome is 1 because now number of ones are odd, this should be even. So no data word is created because there is error. One single bit error changes parity bit. Suppose now instead of, because of error, instead of data word, parity bit is corrupted. This bit is corrupted. Again the syndrome is 1 because number of ones are odd. So no data word is created. Now if error changes a parity bit and a second error changes data bit, then the code word will be like this. The syndrome is now 0 because number of ones are even. There are error in 2 bits. If error is in 2 bits or 4 bits or 6 bit or even number of bits, then syndrome will be 0. So that data word is created at the receiver. Note that here the data word is wrongly created due to syndrome value because syndrome value is 0. If there are errors in even number of bits, even means error can be in 2 bits, error can be in 4 bits or 6 bits of the data depending on the size of data, then it will never be detected by this type of parity code or VRC method, and the data will be transmitted without detection. If 3 bits are changed, now 3 bits means odd number of bits, 1 bit, 3 bit, 5 bits, 7 bits are changed due to errors. The received code word will be like this, which will contain odd number of ones. The syndrome will be 1 because odd number of ones are there. The data word is not created. This shows that simple parity check granted to detect one single error can also find any odd number of errors, but will never find even number of errors. So a simple parity check code can detect an odd number of errors and will never detect even number of errors. So we can say, in other words, that VRC or parity code is 50% efficient, means some errors it will detect and some errors will be not detected. If there are errors in even number of ones, even number of bits, these will never be detected. So there is a probability 0.5 for error detection by VRC or parity code method. Now there is one more method for error detection, longitudinal redundancy check or longitudinal redundancy code. In this, the data is divided into certain fields. Now the original data was having 32 bits. Now the data is divided into 4 parts. Original data was having 40 bits. 8 plus 8 plus 8 plus 8. 32 bits. Original data is having 32 bits. Now these 32 bits are divided into 4 parts. And these 4 parts, parity for each column is calculated by using even parity system. Now 1, 1, 1, 1. There are 4 ones, means even number of ones, parity is 0. Odd number of 1, parity is 1. 1, 2, 3, 4. 4 bits, 2 ones, even number of ones, parity is 0. Here also odd number of ones, parity is 1. So this is the parity code which is generated by using these 4 parts of the data. Now this parity code is added, which is also called LRC, to the original data and transmitted. At the receiver side also, this parity code is recalculated. If it is same, it means data is correct. If this is not same, it means data is incorrect. Or including this LRC, corresponding bits must be even. 1, 2, 3, 4, and this LRC bit 4 ones. 1, 2, 2 ones. No third bit. 1, 1, 2, 1, 3, only 2, 1. So it means these are also even. So number of ones at corresponding positions should be even.